Hi everybody, thanks for joining. It's Brian from Witch Doctor, and today's topic is going to be basic statistics. I realize that I incorporate a lot of statistics in the tests that I do, and it's because I want to have some level of statistical certainty about conclusions that are drawn and recommendations. And so I wanted to do just a brief overview, not in any super detail. This is just to help you be able to interpret some of the things that I say in the videos, or some of the data that I show, or sometimes some of the comments in response to viewer comments. So there is an appendix in Brian Litz's most recent book, The Applied Ballistics for Long Range Shooting, 3rd edition, Appendix A, where he actually covers a lot of this. Again, at a very basic level, and just enough to have the readers, or in my case the viewers, have some degree of understanding about what these numbers are, what they entail. So today I'll go over a brief overview of what's called means, or the average, standard deviation, distributions, statistical distributions, data distributions, t-tests, f-test, or also called ANOVA, power analysis, and correlation. Okay, so what I did is I set up a mock set of data. This is not real data at all. I just sort of made it up. But I set it up so that these numbers in here are group sizes for 5-shot groups. And so in the thing that we're testing is there any difference between primer 1 and primer 2? Okay, and so for primer 1, this first 5-shot group was this size. The second 5-shot group was this size. For primer 2, the same thing. First group was this size, second group, etc. And so there's 5 sets of 5-shot groups here. Okay, so what the mean is essentially the average. So it is the average of so you'll take like primer 1, what's my average? Primer 2, what's my average? Okay. Excel is able to do some basic stats. It is not a comprehensive statistical program. There's many others out there that do a really good job. I'm most familiar with, I don't know if you're familiar with M+ or SAS. I'm more familiar with those statistical programs. They analyze data from numerous different type of scientific paradigms, pharmaceutical industry, medical field, etc., physics, astronomy, all kinds of stuff. But Excel does some basic stuff. So if you do have access to Excel, you can do some of the basic stuff. So what I did here in this Excel spreadsheet is I had it calculate what are called descriptive statistics. Okay, so I went ahead and said, hey, I want some summary statistics. Let's say for primer 1. So I'll go in and do my input range of primer 1. Tell it that it's grouped by columns and that the label is in the first. Oh, no, it's grouped by rows and that the label is in the first column. Okay, and I clicked summary statistics, confidence level for means, okay, and then bam, there you go. Okay, so what I did is I copied and pasted this onto my main sheet because I don't like having 500 different sheets going up. So for primer 1, the average, which is essentially just adding these 5 up and dividing it by 5, the average is 0.2024. And in matches, you'll hear the term aggregate. This is what they're referring to, this is your aggregate or your mean. For primer 2, the aggregate or the mean or the average is 0.2822. Okay, so you can already see that there is, about an 80 thousandths difference here, or it looks like 78 thousandths difference in the average for the 5-shot groups that were shot with primer 1 and the 5-shot groups that were shot with primer 2. That's already a little bit of an indication that, there's maybe a difference here between these two, okay? But we have to conduct a statistical test to see if there's a difference. Okay, standard deviation. It's a bit of a complicated calculation. You can go online, look it up. There's tons of websites that tell you how to calculate it. But what a standard deviation essentially is, in the simplest way, is the average deviation from your mean. So how much in your distribution of scores is there a difference from the mean? Okay. And so essentially it tells us how much is the standard variability in this distribution of scores. So for like primer 1, we're looking at pretty low variability of scores here. You got pretty much low 2s and, one middle and one high 1. Primer type 2, very little variability there too. You got some low 3s and some, low, mid, high 2s. It turns out that in these two distributions of scores with primer 1 and primer 2, the standard deviation for primer 1 is 0.037, so 37 thousandths variation in kind of the average variation in group size here. And actually for primer 2, in the 5-shot groups for primer 2, a very similar standard deviation, 0.037. So almost identical amount of variability around that mean. Okay, so now let's talk distributions. What distributions are your numbers and how they're scattered along the continuum of the mean and the standard deviation of the distribution. So let's get some more light here. There we go, that's better. So for primer 1, the mean was 0.2024. Okay, so that's the average. That's this line here in this distribution. And then with the standard deviation of 0.037, the first standard deviation below the mean is basically 0.2024 minus 0.037, which is 1.684. One standard deviation above the mean is 0.2424. Okay, now if you look at the data, see how the numbers here, these three groups are really close to the mean. And then you got two groups that are kind of one standard deviation above the mean. This is essentially your distribution for primer 1. And then what I'll do is I will show an overlaying distribution for primer 2 here in a second. Okay, it's going to be kind of complicated, but so primer 2's distribution is sort of moved over to the right here, where the average is 0.2822, okay? And one standard deviation below that is 0.2452, which is actually to the right of the first standard deviation for primer 1. So right off the bat there, you can kind of see how these distributions now are taking shapes in kind of different directions. Within the primer 2's distribution, you have 0.236, which is just outside of one standard deviation below their mean. 257 within one standard deviation, 286 and 0.301 again within one standard deviation, and then 331 outside of one standard deviation. Now notice how, just like primer 1, 3 of the values are clustered close to the mean within one standard deviation of each other. Same thing with primer 2. You got 3 values that are within one standard deviation of the mean. Notice too that their distributions are sort of far apart on this continuum of group size. Okay, earlier I mentioned you have to actually test to see if the distributions are different. Okay, so in this simple example of having two primer types, you're testing one type of primer versus the other, and you're looking at group size as your major outcome. You can do a t-test in Excel. In this type of test, what it does, it will tell you the probability that primer 1 is actually different than primer 2. Okay. For this type of test, you would use what's called a two-sample assuming unequal variances. and it's kind of complicated to pick which type of t-test to use because there's a few different types. Like if we go to data analysis here and we go to, there's paired two sample assuming equal, two sample assuming unequal. In an example like this, where you have two groups, you have a primer 1, primer 2, it's a two sample assuming unequal variances, okay? And so you would click OK to that, and then you would add your variable 1 range. So you go to your raw data here, and you say, okay, that's variable 1, primer 1, and then here for variable 2 is primer 2, okay? And then just leave it as is, click OK. Oh. Uh-oh, I have non-numerical data. Okay, oops, I have to put labels. That's why I forgot to click. Okay, now you've told it I have labels in there. The non-numerical data are labels. And then you get this little sheet spit out. I'm going to delete the sheet again because I copied and pasted this already into this first sheet. But this is where you get your t-test. Again, your t-test now shows you the mean for primer 1, the mean for primer 2. It tells you how many of the 5-shot groups you shot, 5 for primer 1, 5 for primer 2. The rest of this stuff, irrelevant. Just what's now super important is actually the probability value here. A two-tail probability is what you want to look at. And what it says here is 0.009443. Now what that means is that there's a 99.0557% chance that the primer 1 is different than primer 2, okay? The industry standard used in a wide variety of research paradigms is that you have to have at least 95% probability that there is a difference. And if you have 95% or greater probability, then basically you have a 95% or greater chance that there is an actual difference. And this is what we refer to as statistically significant difference. So if this p-value is lower than 0.05, then we call it a statistically significant difference because the chances of it being real are extremely high, okay? But, so even if you have a probability value that's below 0.05 and you can tell, oh yeah, this on average is 80 thousandths, smaller for primer 1 versus primer 2, that is good information to know, but you still have to use test methodology that answers a question like, was it really just primer 1 and primer 2 differences, or was there some other factor that was at play? So for example, what if you shot all the groups for primer 1 when the conditions were great? It was very mild wind, if any, temperature was mild, range was quiet, there was no one around, whatever, like ideal sort of shooting conditions. What if you shot all your primer 1 groups in there, and then primer 2 you shot 2 weeks later in a windstorm? Well, the statistics can tell you, yes, you have a statistically significant difference in these distribution of scores, but do you think that that's really due to a difference in the primers? No, it's probably due to a difference in the conditions you shot, okay? What about, all of the primer 1 groups were shot with a cold bore, and primer 2 shots were shot with a hot barrel, and you know that hot barrel shoots worse when it's hot, right? This is why the design of your test is extremely important, okay? You want to rule out all of these, what we call extraneous factors that may produce a difference, okay? So in this example, you want to shoot both primer 1 and primer 2 when the conditions are great, okay? If you know that barrel gets hot and it shoots worse when it's hot, let the barrel cool down. I have temperature indicators on all my barrels for this reason. I know exactly which barrels shoot worse or better when they're hot. I know exactly which ones shoot worse at exact temperatures and all that kind of stuff. So you want to rule that out. You can even change the order for which you shoot primer 1 and primer 2. So if I'm going to shoot them all on the same day in the same conditions with the same barrel temp, I'm also going to shoot primer 1 first, primer 2 second, and then the next set of groups, I'm going to shoot primer 2 first and primer 1 second, and vary the order, because what I'm going to be essentially eliminating is what's called order of effects, when the order of the shooting impacts the outcome. So test methodology is extremely important here. You can't just do shoddy methodology and then, interpret these results to mean primer 1 is better than primer 2. It's, all your methods have to rule out a lot of these factors in order to come to that conclusion, okay? So extremely critical is your method. Okay, one other thing that Excel does is what's called an F-test or an ANOVA. ANOVA stands for analysis of variance. The F-test or ANOVA is essentially the same as a t-test, except when you are testing more than 2 different things. So let's say I tested 3 primers, okay, and we have a primer 3. All right, now I can't run a t-test with, primer 3. Let's say I have, all these values filled in with 3 sets of primers. A t-test is only going to compare 2 samples. The ANOVA is what can compare more than 2 samples, okay? So you would choose this ANOVA here, and then you would give it all of your different groups, your primer 1, 2, 3. There's no values in here, but let's say you did have values. You tell them that they're grouped by rows, labels are in the first column, and then you click OK. Now, what you get then is kind of the same thing you get with a t-test. It'll tell you the probability that there's a difference, but it won't tell you what is different. Okay, so it'll just say, yes, you have a statistically significant difference between, some of these different primers, but you don't know exactly where that is. You don't know, is it primer 1 better than primer 2? Is primer 2 better than primer 3? Etc. So what you have to do is what's called a post-hoc statistical test to find that out, okay? So once you do a post-hoc test, that'll tell you where the differences are. So let's say, for example, in this example, there's a difference between primer 1 and 2 and 3, but no difference between primer 2 and 3. So primer 1, was better than 2 or 3, had the lowest ag, group size ag, but 2 and 3 were the same. That tells you right there, okay, primer 1 is better than 2 or 3, okay? So you have to do what's called a post-hoc analysis. Now, Excel does not have that capability to do a post-hoc analysis. You have to actually get either more advanced statistical setup, or you have to find some kind of website that will calculate it for you. Okay, I'm going to review a concept called power analysis. It's essentially a statistic that tells us how much shooting we need to do, okay? How much shooting do I need to do to be able to detect whether a difference in whatever I'm testing is statistically significant, okay? This could be a pretty complicated scenario if you don't have previous test results, all right? So if I don't know kind of what I would expect in terms of, how big of a difference I can, I'm expecting to find, then it's hard to do a power analysis, okay? This is another reason why I go over my statistics quite a bit in these videos, and hopefully will in a book soon, is to provide shooters with previous data so that if they go and do their own tests, they'll know based on my results like how much they need to shoot, okay? And what a power analysis is, like here's an example of a software that does a power analysis for you. You have to input what's called your expected effect size. Okay, so how much do I expect these two distributions to be away from each other and have small standard deviations. So it's a bit complicated, and you need previous, testing and data to sort of even go to something like this to input data to see how much shooting you need to do. The general rules for it is that you need to all you need to do is just shoot a little bit when your averages show large differences and you have the same or lower standard deviation. Okay, it's kind of like this example. We have we have 80,000 or 78,000 differences in our averages between primer 1 and primer 2, and almost the same exact standard deviation. So I can tell you right now that looking at this data without even running a t-test, I know it has pretty good statistical power because we have a large difference in the average means and we have the same standard deviation. And what we found is that it did have a statistically significant, effect. So essentially, this test had enough power. You only needed to shoot five-shot groups between primer 1 and primer 2 to detect that there is a statistically significant and meaningful difference in these distributions. Okay, so this test, I always tell people, well, don't you need to shoot 800 5-shot groups? It's like, well, no. If you have the statistical power to detect a difference, then you will detect it, and you just need to shoot the amount that gives you the right amount of power to be able to detect that difference. Now, if you're looking for a small effect, you're going to need to shoot a lot more. So you'll need to shoot more when the averages are usually small, and standard deviations that are either the same or higher. So let's say this average here ends up really being like a 0.2120. That average is not much different than 0.2024. Standard deviations could be the same, but I'm going to tell you right now, based on my experience in running these kinds of stats thousands of times, that's not enough power to detect a statistical difference. I would have to shoot several more 5-shot groups in order to make 10 thousandths of an inch statistically significant. Okay, but since it was 78 thousandths of an inch, it had the power to say, yes, there is a meaningful difference here in these two distributions. Okay, so that's statistical power. In a nutshell, you do not need to shoot 5 billion groups if you're testing something that is known to have a pretty large effect. Okay. This definitely is important for testing because, let's say your power analysis says you have to shoot 200 5-shot groups to detect a difference. Well, at that point, you've burned out a barrel. Not to mention how much range time you would have to do. How do you eliminate other factors? Shooting 200 5-shot groups, you're going to have to wait for your barrel to cool, clean between sets of group shots. You're going to have to match shooting conditions, all kinds of stuff. So chasing small effects is, to me, not worth it because I end up, using more resources to find a small effect, whereas I would rather use little resources to find larger effects. Okay, and most of my testing to date has been on things that I anticipate may have a larger effect. I've certainly done some things that have had no effect, and like the most recent flash hole size test had no effect. I mean, there was nothing, but I did shoot a lot of bullets. But I stopped that test after I ran, 6, 7, 8 sets of groups. Because it's like, if I'm not detecting a difference at this point, I'm just going to stop running this test because I can go down the rabbit hole of, having to shoot like 84 5-shot groups in order to detect a difference. Okay. So there's some practical decision making that can help inform you if you're going to do testing from a power analysis. Okay, correlation is a statistical method that is used to see how much two variables are related to each other. So for example, let's say you're wondering whether changes in seating depth lead to changes in average velocity in 5-shot groups, okay? So you'd set up a test where you shoot several 5-shot groups, all with the same powder charge primer. You control for all these different variables, shoot them all on the same day, clean out your barrel, let it cool, etc. And then you shoot these groups all in different orders. And your first set of groups is touching the lands, and then you test another set off 15 thousandths, off 30 thousandths, off 45 thousandths, all the way up to off lands by 90 thousandths. Okay. And then you collect all your average velocity data from, lab radar or whatever you got, to get your ballistics. And then you put them all into a spreadsheet, and Excel actually does correlation. So you can do that in Excel. It's under what's called regression, and it allows you to pick 2 variables. So in this example, you would pick how the interval for how far on or off the lands your bullet was, and then your other variable is going to be your average velocity of your 5-shot groups. And then you click OK, and then it gives you some statistics. The statistics that are important in this analysis are the R squared, and the p-value. The R tells you the direction of the relationship with the variables. If the R is positive, then an increase in one variable is associated with an increase in the other. The R squared tells you how much of the variance in one variable is accounted for by the other variable. And finally, the p-value is the same as the t-test or f-test in ANOVA, where if the p-value is less than 0.05, if your p-value is greater than 0.05, then the R and the R squared are meaningless, because you don't even have the industry standard level of probability that the correlation is not due to chance. Now, if the p-value is less than 0.05, then the R and the R squared are interpretable. Okay, I actually did this test of seeding. I found a statistically significant negative correlation where one variable went up while the other variable went down. My R value was negative 0.966, which told me that there was a pretty significant and tight relationship between seeding and average velocity. The probability value was 0.0004, which means that it was a statistically significant correlation. Basically, as seeding depth increased, so the more I seeded the bullet into the case, velocity decreased. Okay, and in that test, my R square was 0.9332, which means that an increase in seeding depth accounted for 93.32% of the variance in average velocity. So 93.3% of the changes in velocity were explained by seeding depth changes. In R squared, that large is extremely meaningful. You really don't get R squares that high. So that told me that yes, if you are going to be, testing seeding depth to where, you're looking at 15 thousandths or more changes in seeding depth, totally expect velocity to change. And the more you seat off the lands, the lower the velocity is going to be. Anyway, that all has practical, implications, for how you do your, load workup and all that kind of stuff. Anyway, so that's it. There is another type of correlational sort of statistic called regression, multiple regression, which is basically looking at the relationship between more than 2 variables. It's looking at, if you have 3 or more measured variables, how do, they relate to each other when you're controlling for other variables. That's kind of a more advanced topic, definitely not for the context of this video. There's also statistical modeling, structural equation modeling, all kinds of, growth forecast modeling, all kinds of stuff that we can get into here. But that kind of advanced modeling would be useful for larger, more comprehensive testing that incorporates multiple factors into the testing, which is something I'm hoping to, do here in the near future with a lot of this testing. But anyway, I've talked a lot. If you have extreme insomnia, just keep watching this video and I guarantee you it'll put you to sleep. Thanks everyone for tuning in. Please like, share, and subscribe. Also check out my Patreon and help me out if you can. Provide some support to continue these tests. Not just the testing, but my equipment, my camera I use, software that I can run good stats with. There's all kinds of things that go into these tests, lots of expenses. So any kind of support you can throw at me is appreciated. Thanks everyone.